There we go. Now it's going.
So could we come back very quickly, just for those who may like?
Yeah.
Oh, thank you very much, by the way. Okay, we did nothing almost. So again, hello everyone. So what we are going to do is that we are going to start our AI classes. And now we are familiar with the definition of AI. And we are going to start with search problems. So in search problems, we need to have some kind of terminology, and we need to master some new taxonomy. The first thing to know is the definition of an agent. And here through different examples, for example, if we are having a car going through the map, there is this point is representing the destination, and in this case, our agent is this car. In another example, the agent is the cleaning robot, which is moving and having its specific moves. In another example, or in the chess game, the agent is the player, or you, or if it's a machine playing. So it takes it's the one deciding which moves to take in order to win. In another example, we were going through the Super Mario game, where the main objective or the main goal of this agent or this representation of the Super Mario is to win or reach to the queen. Another example is this delivery drone, or in your case, so everyone is the agent of his own life. So moving now to, or let's say that the clear definition of an agent, it's the entity that is taking decision, or more formally, it's the entity that perceives its environment and acts upon that environment. Here we have the agent is perceiving the environment thanks to sensors such as cameras, microphones, and so on. And it's not only going to perceive the environment, it's thanks to a program within the agent, which is going to have, for example, specific algorithms to execute, and based on that, the agent is going to behave. When I say behave, it means acts and take specific acts thanks to actuators. Okay. The second terminology is environment, which is the world in which the agent exists and operates. The environment here, we distinguish 6 types of environments: the fully observable environment, partially observable one, the deterministic, stochastic, episodic, and sequential environments. We were moving through a different definition, which is the definition of a state. The state is the given configuration of the agent and its environment. And in this example of 8 puzzle game, we have this random given state is called an initial state. Is from where the agent is going to begin and start its game. Then going through multiple intermediate states, the agent is going to reach or to come to the goal state, which is the ordered elements right here. So different actions could be taken, and they represent the choice that could be made in a state. And here we have, this is an abstract definition. In order to make it applicable or programmable within program it within a computer, we need to assimilate it to mathematical function. Here the function is called actions of S. This S is the input, which is the state, and this action of S is going to return the set of actions that can be executed in a given state S. So the different actions here, for example, slide to the right, to the left, up or down. And for a transitional model, for example, we have also the definition, which could be also given by a mathematical function. It's called here result of taking as input S and A. S is the state and A is the action. And this result of S and A returns the state resulting from performing action A in state S. Okay. And so the transition model is a description of what state results from performing any applicable action in a state. We took few examples. We went through the first example, which is taking this function given this this state where we have the empty spaces in the middle, and what action to take is to slide like one of the numbers to the right. So the only possible thing is to slide the number 5 towards here, which is going to result to this transition model. Okay, this is the result. There is not only one. We were going through different examples. If I'm going to move it down, I will have an empty space here, and this is the result given by the function result or the transition model. Another time, if I will move here, I will find this result. So as you can see, guys, we have multiple obtained elements from that result, transition model. So this defines the state space, which given each action, given each possible state, what can result. Okay, so here this state space is the set of all states reachable from the initial state by any sequence of actions. For example, from here to here, I can go thanks to this arrow. I can also come back to the same state. From this state, I may choose a different action to take to find myself in a different transition model. So I can again come back, and from each one I can go. And this is just a representation. The state space is bigger than this. Okay, so we went now through these definitions of agent, environment, action, transition model, state space. Okay, and now we want to think of this problem given a more complex situation. In the start, what we see is that this car is moving towards the destination, and it's very simple to drive straight and go. However, in the real life, sometimes you may find the road blocked, sometimes you may find some traffic there. So in order to reach your goal or your destination, you may think of different ways or paths to come there. Okay, so this is one possible way. Another way, for example, is to take this one. Or sometimes, because maybe we don't know, we can go from this way, find ourselves blocked there, and the road is closed, for example. So these all are situations that may introduce uncertainty, okay? Because we don't know. Is that clear? So in this case, what we need to do is that we have to execute plan that could be different from our expectation. And here in most of the real world problems, we deal with the uncertainty, okay? So how to solve this, we are going to discuss that later, but at least how to represent that, we are going to see this right now. If, for example, I have the same problem, and I want to move from one position to another, we suppose that everything is possible, okay? And I can represent where I could be as nodes. This is the final state node, which is the goal state, okay? And this is my initial state from where I'm starting. To go from here to here, I might go with this intermediate state. I may choose different available possible nodes that may take me to my destination. Is that clear? Okay, so here I am introducing a concept of node, okay? And please feel free to let me know if you are not familiar with, for example, data structures or some concepts or something, okay? So if, for example, I am going to move from my initial state towards the goal, it has some cost. If, for example, you come back and remember the way that I was showing in red there, what is the difference between the red one and the black one here?
Longer.
The shortest path is the black one.
I cannot hear. One by one? Yeah?
The shortest path is the black one.
Shortest path. Okay, yes?
The red one is longer.
So the red one is longer.
Time also.
Time. So distance? time,
Cost of.
fuel consumption, for example, money. Okay, so there are a lot of factors to consider. It's not just I need to reach to my goal. Sometimes I need to think of the cost to reach to that goal. So as given by the representation now, what we will have is that it's not only the nodes are connected, okay, and they are connected via these like arrows, means which represents the direction. For example, I can go from here to here, but I cannot go back from here to here. Is that clear? I can, for example, go from this node to this one, but I cannot come back to this one. And the cost of going from here to here is equal to 2. I don't know, $2. But we have here different costs, okay? So this is one like possible representation where it's really like more realistic but more complicated. At some situation, we may consider that all the arrows are having the same weight, okay? And this weight is equal to 1. So whatever action I'm going to move from one node to another is just 1. For example, like the 8 puzzle we are going, we just seen right now, let's consider that the cost is just one move, for example, okay? So this is the past cost. So now, in order to define the problem in like AI for sure, the problem could be defined given a state space, and the state space here is the possible states, including initial state and goal state. We go from the initial to the like goal through different intermediate state, or like we represent our transition model, and we have different possible actions to be taken, and for each action we have for sure the transition model, as I was saying. We were also introducing the path cost, and the path cost is the summation of the step cost, means the cumulative like sum. For example, if we go back to this case, if I want to go, let's take a clear one, from here to here, what is the path cost? 2. It's 1 plus 1. We keep like the sum each time. Is that clear? Okay, so here we are coming to our definition of the problem, and for sure the goal test is to determine if a given state is the goal state or no. So I was reaching to that point where the cost was 2, but is that the goal state? If not, means I did nothing. Okay, so moving now to the first example. So I was sharing in the classroom few quizzes. I think you guys have access now. So try to, you have your laptops. For those online also, it's accessible in the classroom.
Yep, I saw 4 of them, I think.
Just let me know if you can access the set of quizzes.
Yep.
So you start taking. Just to explain, so now we are going to have four quizzes. The first one is the 8 puzzle we are just discussing right now. And there is a description provided for each problem in the canvas. So this problem here, what we have is just this like 2 like representation. The first one says that this is the start state. The second like image says that this is the goal state. Other than this, I don't know. I know nothing. So what you are going to do is that each time, and for each like case, you are going to find the states, the actions, the goal test, and the path code. So in order to help you, I am giving you like possibilities, but it's not in the order. So among these, you try to guess which is the state, which is the action, which is the goal test, and which is the path like cost. Okay? So very quick, in 1 minute, I'm sure that you can do it. If you are good with the, like you are understanding what I'm saying. If not, it's my job to do it again. just the first quiz? Just the first quiz? Yeah, okay, we can go one by one together. Don't go to next quizzes until we solve this one together. Otherwise, for those who are going to watch this recording later, just pause your video, answer your quizzes, and come back.
Is anybody else online having trouble getting to it?
No, looks fine to me. You know, before I read it too closely, I thought we were going to have to try to like solve it ourselves by moving all the tiles around and then like have you show us that AI can do it much better. And this was much more pleasant than that.
I wish I was finding one. I was trying to find, actually. I didn't find anyway. You have one?
I completely read this wrong.
Yeah, me too.
Yeah,
Done?
yeah, I'm done, but I got a 0.
Oh my, no.
I read it wrong.
How
I
come?
looked at the board.
You
It
show
makes,
me?
it makes sense now.
Oh,
I just looked at the board and saw that.
I was-
Saw that's what we were marking
I was
down.
saying that it's not in the order.
I didn't hear that correctly.
Okay, so. Okay. You guys are good. No, actually, the idea is that we are going to select what is the meaning of a state. What is a state? We were just introducing and defining a state. So is a state a move like blank left, right, up and down? Moving something is a state or an action or a goal or a path? Is an action to move or the action is already given in the situation or the action is just one per move or the action is the location of that? So path coast, is it this or this or this or this? Just to select. So is everyone done with this? We move to the,
Can I redo it?
I think no.
No?
I think we need now to move. So what is a state now? You cannot do it again, but you can do it now. Yeah. What is a state?
Location of time.
Yeah. So the given location of the tiles is a state. So this is a state which is called the start state, and this different location of the different tiles is different state, which is the goal state. As simple as this. So what is the action? In general, even if you may see this in the exam, actions always starts with a verb. I can do something. I can take some action. So here I can move it to the right, to the left, up and down. So these are the possible actions. What is my goal test where I want to be or reach? The goal here is to. What is it? Show me the goal.
Is it the goal?
Yeah, you can show me the goal if you can.
Yeah.
You can come and show me the goals. Yes, that's the goal. Is it clear? So it's given. So this setting is the goal. And what is the path cost now? One per move. So it's going to be equal to 1. So now I believe that the concept is clear for everyone. And I will expect better results for this example. This is the correction. But if we will consider the 8th queen, You can go to the classroom. There is another quiz and try with this one to make sure that all these concepts of states, actions, goal state, and path codes are clear for everyone. There is another quiz now. And for those who are online, pause your video, finish your quiz, and come back. So we have again the states, actions, goal states, goal test, and the path codes. What suggestions we have here or definitions? Any arrangement of 0 to 8 queens on the board. What is this? Or add a queen to any empty square. What is this? Something is not given. Could you guess what is it? And 8 queens are on the board, non attacked. What is this? Just let me know once done. So we move to the correction. Are you done? Done? Is it hard? Now, better?
100%. I understand it this time.
Okay, great. So what are the states? So any arrangement of 0 to 8 queens on board is going to be the given state, okay? And we don't know here if the given one is the initial, intermediate, or a goal state. We don't know that, okay? The action that we may take is to add a queen to any empty square, okay? And the path code, we don't know in this case. And the goal test is to have 8 queens that are on the board. None is attacked. As simple as this. So you can now move to the next quiz, which is the case of the vacuum world. The description is always in the canvas. So no dirt, 1 per action and 0 for no operation. Left, right, set no operation, and dirt and robot locations. Guess what? Now you must make it really fast. Done? Any questions?
I think one of your questions is wrong.
It's
Pat-
like
Path cost says the correct answer is something that it shouldn't be.
could happen. So I will fix that after this session.
Okay.
Okay. But that's a good sign that you guys are getting it. Okay. Done? Okay. So the goal test is to have no dirt. What was mentioned in the right, like, or the wrong?
It said path cost was no dirt.
Okay, so that was a mistake. For us now, the states are dirt and robot locations. So this is a given state and this is the other state, for example, A and B. The action that could be taken is to move right, left, side, or there is no operation taken. And the goal test is to have no dirt, that means to clean. The path cost is 1 per action and 0 for no operation. Okay? So I'm sure that now everyone is getting it. Having this kind of quiz in the exam must not exceed like 1 second. So, yeah. It's from me and then with that after the session. Yeah. So you must be very quick with this like concepts because now you are familiar with. So try to test yourself with this example, which is also available in the Canvas, the last quiz, which is the Pac-Man, which the main goal is to eat as maximum points as possible. And just have done, all of you. Are you like doing that in the Canvas or just no mental thing? Oh, try to do that online as well. Yeah, no worries. It's open until next week on cases. So it's supposed to be done for everyone right now. Any mistakes here for those who are done? I'm not sure.
2.
Oh, okay. I trust you guys. Don't trust me.
Also in the
Yeah, this is what they're saying. Okay, that's great. So now I'm sure that you guys are like perfect. So what are the states in this case? So
Position on the back leg.
okay, and different possible actions.
Left foot down.
Okay. The main goal is to eat all like dots, and the path cost is each time we're eating 1 dot, we get 1 as a reward, and dead after being eaten by a ghost. Is that clear? So now I'm sure that we can move to our problem solving agents and searching for the solution. Now we are understanding these concepts, so we are able to start with the search algorithms. Search algorithms are a given solution or a given set of actions that is going to take us to the goal. And it's not only that we are looking for a solution, as we were discussing, this solution must be optimal, means we reduce the cost as max as we can, okay? The best possible solution, in other words. Is that clear? Okay, so here we introduce search algorithms that are going to work by considering various possible action sequences. And we are going to select the optimal one. It's based if our algorithm is optimal or not. It's an like performance metric of each algorithm, because we may see some algorithms that are not optimal. They find the solution, but they go through a very long way, okay? So then if you are familiar with data structures, you may see something called tree before adding the word search. So is everyone familiar with the concept of a tree? Okay, for those who are not familiar, a tree is where I have a root. It's the starting node. From that, I can take different branches. We may consider the very simple example of a binary tree when I only have, for example, to go right and left. It's like balanced tree, like, for example, this is my main, or this is my root node. I am going to go whether to the right branches or the left ones. At this given position here, I have a child, and here I have another child. So each child now is having a parent node, and we are going to see this later. So is this like clear for everyone? We are going to deal with this kind of representation. The tree at some positions may not be like perfect. it may not be like a binary tree. We may have possible different like nodes to go from a given node. And so just this is needed to understand the remaining of this course. So what we will do now is we are going to consider a search tree, and a search tree here, if we are going to map that to the concepts now we are learning, this kind of tree has as initial state the root. It's the first state where you are. Then it has what actions you will take, means what branches you are going to choose. And the nodes are going to correspond to states in the state space of the problem. Is that clear? Okay, so this is if we are going to represent the problem from like algorithmic way, we can solve it. So we will go now or take a real, like a very famous example, which is the traveling in Romania. This example is very famous. And the idea here, these are the different states in Romania. And what we want to go is we have our initial state, the root here is this like city is Arad. And our main objective or target is to reach to this like node, which represents a city called Bucharest. Okay, so different actions are going to be taken, and we can consider different search algorithms in this case. So the very basic one is the search tree algorithm. So in this case, what we have the tree search algorithm. It's a function. Given the problem, we are going to return the solution if it exists. Sometimes there is no solution, there is no goal. We are not like coming at any like expected point. So we will return failure, means there is no solution. So the idea is to first initialize the frontier using the initial state of the problem. So what we know about the problem is where we are right now, the root. So we are, for example, in that state. What was the name of that state? Alright. So that is my initial state. I will put that in, we will introduce this later in a data structure, and then we are going to loop. So if the frontier, it means the data structure in which I am keeping my states is empty, which means there is no solution. Okay, I have no node, there is no solution. And what to do in this case? We are going to choose a leaf node and remove it from the frontier. Clear?
What's a frontier? Is that just what you initialized your in?
Yeah.
Is it just the name?
Yeah.
Okay.
I said for now, consider that as a data structure.
Gotcha.
If this data structure contains one element at least, which is the root, we are going to check. If this is like something is there, we will see what to do. If nothing is there, there is no solution. If something is there, we keep like following the leaf nodes and each time remove from the frontier. Okay? If now the node contains a goal state, so we are going to find we are coming to the final node that we are estimating, and otherwise we are going to expand the chosen node, adding the resulting nodes to the frontier. I still have nodes to explore, and I'm still not coming to the final goal, so I will keep exploring. So I will keep exploring by adding that to the data structure called frontier, okay? So the frontier here, so it's a data structure that is going to represent the set of all leaves or nodes that are available for expansion at any given input. Like, for example, in this case, I am at this like given node. What I have in the frontier, in the start, frontier is empty. Imagine it's data structure. You are going to save like your elements there. The start, we will put the initial node. Now I have an element. From this element, what possible other nodes that I can explore? I have this one, this, and this. So it's 1, 2, 3, 4. So my frontier now, each time I am going to explore one node, I am going to like save it in this data structure. Then again, from this point, for example, here, I have no element, so I will not add anything to this data structure, to the frontier. If here, for example, what I will add, I will be adding this element and this element to the frontier. Is that clear? So for now, the frontier is the data structure that is going to contain all the set of leaf nodes that are available at a given position or a given, like from a given node. Is that clear? Please. Sure? Okay. The problem now, or before moving to the problem, we were already having that example. Let's think of executing this in this case. So I have now my initial like state is this arad. So I'm going to add that to the frontier. What I have in the frontier, I have this from here. What or which nodes I can expand, where I can go from this position. I can go here or here or here. Is that clear? So these are going to be visited. And if I would be thinking from an algorithmic perspective, so I am going to add these nodes or these cities to the frontier. Is that clear? Which is a data structure. Having all the nodes that we can explore from a given node. From this node, for example, I can explore this one and this one. And if I want to keep this representation, so I will store that in the frontier data structure. Is that clear? Okay. Now, let's think of this. From this like point, or from this city, I can go to this one, I can go to this one, or I can go back to Arad. So if I will go back to the main point, what is the problem?
Reach the goal state.
This?
You can't reach the goal state before.
Yeah. Oh, but I can reach after.
The
Because-
path should be more.
Yeah, I can maybe not reach at all because this loop could be an infinite loop. And here we did nothing. You understand? So if we are saving the visited nodes in some data structure, and at some point we keep visiting them, means there is a redundancy like problem appearing, and this will not let us come to the final goal. To solve this problem, which exists, so we need to adjust the algorithm of the typical like search tree. So what we will have is the new version is the graph search algorithm. It's mainly the same algorithm. So in the start, we have the function. We have initially the frontier we initiated based on the explored set. It's empty. Then we have this loop. If the frontier is empty, then we return failure. There is no goal at, to reach. Otherwise, we are going to choose a leaf node and remove it from the frontier to keep exploring. And if the node contains the goal, there I'm coming to my final state. This is what I want. So I'm going to return the corresponding solution. Otherwise, before we use it just to expand the chosen node and add that to the frontier. This is the previous algorithm. What we did, we are adding these two lines, and the first one is to add the node to the explored set. So we had the frontier. It was a data structure introduced to know from a given node where can I go, the upcoming explored nodes. Is that okay? Now, if I am exploring one node, to avoid going and coming in an infinite loop, I need to have track of what I have explored. And this will let me avoid like visiting it again. Is that clear? So adding this means we are going to add the explored set in a data structure. We are going to store that in order to remember every expanded node to avoid redundant paths. This is what we did. We are just adjusting the algorithm. So it's from a very basic search tree algorithm going to be applicable on a little bit complicated graph search problems. Is that okay? So in this case, from arad, we can go here, here, or here. And at this level, I cannot go back because I'm having that stored in that new data structure, the explored one. So I will explore new and visited cities. Is that clear? Okay, so here I am exploring new and visited cities, and all this must be also stored in some other data structure, which is called a node. So a node is having 4 elements. It's a data structure that keep track of 4 information. What? All okay?
Yeah.
Okay, great. So we have track of all information. The first one, first of all, is the state. I need to know the state. So the state in the state space to which the node corresponds. I need to be aware of this. The second thing, I need to keep track of the parent, which is the node in the search tree that generated this node. And here I'm coming with the good memories or souvenirs of the story of these 2 guys. They are called Hansel and Gretel. So they are the 2 famous guys that went from their house to the forest. And each time they were throwing the bread like pieces or breadcrumb in order to track the way back to their house. Okay? So we need to keep a track of something. But if you will not save that in the explored list or in a given data structure, it will happen what was happening to them. So you will get lost. This is why you need to be aware of the importance of the explored like set, which keeps the track of the parent. Okay? And also we need to keep track of the action, which are always like applied applied to the parent to generate the node. Also something else we need to keep track of, which is
Good. Good.
the goal is a state.
Yeah.
So if I'm saving the states here, I'm saving the initial, the intermediate, whatever we are, including the goal. But the very important information that I need to keep is the path cost, okay? So the path cost is the path from the initial state to the node as indicated by the parent pointers. As we see, some pointers could have the same like cost, which is 1. Some may have different costs, 5, 9, 6, whatever. This cost could be, for example, the distance in kilometer. It could be the fuel consumption. It could be the time being taken to reach to the goal. So a node contains or track information of these 4 important elements. Is that clear for everyone now? Okay, so this is a representation of the node given the example of the 8 puzzle. So the node here is going to have, for example, this given state as track of the state. We need to have information about the parent, which is the produced from this state. For example, this state is coming from, for example, it was empty here or empty here. Next, we were making the space coming. Is that clear? Means the step before this state. You can imagine that, the previous state. And also we need to have like a track of the path cost. Path cost is the cumulative sum of actions that I took until that position or state that I am currently in. For example, here it's 6, which means that I was moving 6 tiles to come to that position when we are at this point. Is that clear, please? Okay. And we have the action, means at this state, what possible action that I can take? I can move it to the right. Is that clear? Okay. So this is an illustration. Let's come back to our example. So from the Arad city, we can visit these 3. Then cities. Then we need to know with what order, for example, to use, excuse me, what order to use to choose between these 4 elements. Now, if you guys, no one was like asking me the question, but previously I said from this point, I can visit this city or this city or this city. And it's myself who decided that from this city, I can go here, or come back. No one was saying why you are starting with this city. Why you didn't say, I will explore this one first? Or why we didn't explore this one first? This is a very important question. So the choice of which city to explore first is very important. And it is part of the search algorithm, okay? So here in our case, we are going to see multiple search algorithms. Each search algorithm is going to focus on a given like setting or a given like algorithmic definition or we say setting, okay? So for example, we will see among the algorithms, for example, BFS. Keep this in mind, please. So the BFS is the breadth first search. So this algorithm uses a different data structure or like logical way to deal with the elements that are stored in a given data structure, which is the FIFO Q. Okay, I will come back to this. We will also see another algorithm, which is the DFS, the deep first search. And this algorithm is like taken into consideration the logics given by FIFO. And it's a stack. And we will also see the greedy best first search, which is an algorithm that considers the priority queue. For now is this, but okay. Now we need to understand concepts such as FIFO, LIFO, and the priority queue. Are you familiar with these concepts or not first? Anyone who? Okay, so the FIFO is representation of the queue. Like you are going to the bakery shop. Imagine this is the shop. I don't know if it's clear for those online. You can see me and my bottle and my stuff.
Camera's having a little trouble following you, but I'm familiar with it. I don't know if anyone else is.
So you will imagine. So you imagine that you are going to buy some pizza style. So you are going to find some people coming before you to the queue. So what will happen is that you are going to come the last one to the queue. So you need to wait for your turn, okay? And the logic behind this is the first one coming is the first ones being served. This is why it's FIFO, first in, first out. So it pops the oldest element first, okay? And we are going to explore now a tree, for example, and we are going to start this one, this one, this one. I will consider the order. So I will be exploring in order. So I am going to explore like this first. Then I will move to the next explored ones. And this is the breadth first search algorithm. So this is how, if you will see the tree elements are visited, it will be this way. Okay? Okay. So the second one is to have a stack. And having a stack, it means it's different structure from a queue. And for example, here is the stack where I can store my visited nodes. For example, this one is visited first, so it will be at the bottom of the stack. Next this, and next this one. So if I will be visit a new one, it will not be the last one like the queue. It will be the first one that I was recently putting. It will be the first one that I am going to treat. And if I am going to apply this logic, I am going to be at this point, then I'm visiting this one. This one I'm visiting first, then from this one I will explore. I will come to this one. And again, this same one is the recent one. I will be also visit. I will be also visit. I will be also visit. I will find myself going in depth. And this is why the algorithm that we are going to see is called DFS, depth first search. Another algorithm is going to get rid of the problems that we will see. There are like limitations of each of these algorithms. So to find a solution, we will be thinking of the priority queue. It means we are going to have some heuristics, some evaluations, some function that may give priority, like for example, in the previously introduced pizza queue. For example, if, I don't know, someone is coming with a baby and the baby is crying and wants pizza, I believe that they may give him priority to say, oh, you can get it first. Okay, so this is for now, and please let me know if it's not clear, because everything will be based on this later. Great. Online? Okay. So next, we have this data structure that is going to stock the explored elements, and this is going to be represented as a hash table. If you are not familiar or you forgot, hash table make kind of a representation. Is going to tell you if you have a node, if this node is visited or not. For each value, we are going to have like key value, and the key is the node, and the value can be visited or not visited, for example. So like this, we will be able to represent this kind of search problems to our like AI, and there are different strategies in this context. The strategy is defined by picking the order of node expansion and evaluated along the following dimensions. So later we will be having tables. Each time we will introduce an algorithm, for example, the BFS, DFS, A star, or whatever. We will ask questions. We'll say, is it complete? Is it complete means we need to answer the question. Does it always find the solution if one exists? Because some algorithms keep searching for the solution and they do not return any. Or we need also to check the time complexity. The time complexity is the number of nodes generated or expanded. And the space complexity, which is the maximum number of nodes in memory, and the optimality, which to answer the question, does it always find a least cost solution? Means, is it the best, less expensive solution, or it's just a solution which just we can find a better one? Okay, so keep this in mind. And here also in the tables, you may see at like the end, we may have like some notation, like for example, B in order to measure the complexity of time and space, which is the maximum branching factor of the search tree, D for the depth of the least cost solution, and M for the maximum depth of the state space. We'll see this later because we'll have the final equations that represent the like order of n, how much is the complexity. Otherwise, we can distinguish between two types of search algorithms. The first is the uniformed search, and the second is the uninformed search, and the second is the informed search. And here we have the information or do not have the information. Or what I mean, if I don't have the information, it's going to be a blind search. I'm just trying to find like a stupid. Or if I have like some minimum logics or idea about, for example, I want to go from that door. It's not like I will keep moving. I need to have in my brain that the door is somewhere at the left side of the class. So it makes no sense that I'm coming to the right side of the class. Some algorithms do this. So what we will do also, so these different types of algorithms, search like categories, introduce like different algorithms in each case. We are going to treat that one by one. For the informant, as I was saying, it introduces like some strategies, some tactics, some like idea or knowledge that we have in order to find the goal, and that is in general the promisingly, or it's the heuristical like function that we may have idea about. So now, so we are done with this. We will move to the uninformed search algorithms. So uninformed search algorithms may include the BFS that I'm mentioning there, that is based on the FIFO-Q structure or logic. We have the uniform cost search, we will see later, and the depth first search. So we'll see these three algorithms. So we start with the BFS. So the BFS, as I was showing you here, so I am going to move like through the first in, first out, first in, first out. So I am going to visit the elements of my problem, let's say, which is a tree here, which is a different problem here. So I am going to visit it based on level. If I'm done with the level 1, I am going to move to level n+1. Is that okay? So the strategy is to expand the shallowest node first, and we implement it, as I was mentioning, based on the FIFO-Q. And here, let's see. So from ARAD, in the start, I have the total freedom to choose. I can visit this one, and this one. Now, given the BFS, what next I can visit?
I don't know how to pronounce it.
Okay.
It's mentioned here, the BFS in your dreams tonight, you must see BFS FIFO-Q. FIFO means the first one we have visited is the first one we are going to expand. So the first city we were visiting is the first city we are going to expand. Okay? That much you will love AI. I think you'll be seeing me in your dreams. Okay, hopefully. So next, from this city now, where we will go? You try to guess. That is the logic. The FIFO.
Okay.
Which one now?
Okay.
Now where we will be? So from this city, where we will be? Or here. We have, so this is, we are exploring all the elements.
What idea?
Now the next one to explore all its elements is
What idea?
because if it's not clear, let's write. So you need to keep track of the order. The order is, this is number 1. I can write it. I can write. Okay. So what to do? Wait, you need to keep the track. So which one I visited first? Okay, so you know what? You will take track of the first one, Farah the second one, Ayub third one, and do not let someone coming after you to visit the nodes, okay? So the first one is this,
Yep.
the second one is that, the third one is that. Now, which one will explore? FIFO, first in, first out, the first one. So the child of this one. Next, which child is in the least waiting in the like expand? You are right. So it's, we will need to visit all the childs to move to the next one. So this one and this one. Next, which one? Oh, this one had a third child, excuse me, okay? This one has 3 childs, okay? And now, from you, we are visiting this one. Sorry? Okay, this one was impending list. And then, from this one, from this one, this one, this one, and this one, it has this one, okay? So, in this order, based on the first in, first out, we are reaching to this destination, but we were visiting, see how many cities. So it's not an optimum like algorithm. We'll come back to this. Okay, it's visiting, exploring all. And we will see this with a different example of the tree we are just doing right now. So I will be visiting all the elements in a level. Once then I will move to the child. So once then I will move to the next level and so on. Okay, so here I'm at point A, then I will be visiting B because it's the first one I'm visiting. Then I will be having the C. Once the C is done, I will be going to the D. Once the D is done, I go to E and so on. If D is the goal state, then that is why we are stopping probably. Okay, so now I will keep you with this example, which is BFS on maze. So try to think. No, just we will, for those online, you just pause and think how you are going to reach to the goal. And here we are going to think together. So we have, this is our initial state, and this is our goal, okay? And in this like maze, we have this like dark, let's consider them like walls, so we cannot go through these dark like walls, okay? Otherwise, it's possible to take action from any possible like way you can think and reach. We will not take any possible way. We need to respect or execute the BFS algorithm. So how the BFS algorithms work, I have this like element, this initial state, from which I can go like up, down, right, and left. So I can visit this state, then this one, and this one, okay? Next, which one I will go? The first one must always take his right. So from here, I will go visit this one, up or down. Who is in the list waiting? That was the first one after this. It's the 2. So we visit the child of 2. Then it's the 3. So we visit the child of the 3. Then we have the 4 is waiting. We visit each child. So here the numbers give you idea about the order. Means now what you will do is you will see that the 5 or 6, which is coming first, for example, it's 5. 11, 7, 10, 9, which is coming first? It's
7.
I see 5 here. No. 5.
We did.
The child. We're going to explore. Okay. So here we have between 11, 12, 10, and 9. It's 9 of, there is 7, sorry, in the list. Is that clear? The 7, we are not visiting the child. So we need to visit because it's in the queue. And we respect the first in, first out. So after that, who is in the queue?
9.
9, you are right. It will take us to 14. Now in the queue that is coming before 14, we have the 10.
The 9.
What is the 9? The 9. Also, it has another. Excellent. Another chart to explore. Now 14, 15, 13, and 11. We will go to this side now.
12.
Now we have the 13 is in the queue.
12.
Where is the 12? Well, 12 or 13 is one of them. Both are taken to the same one. It's like we are going, you are right, to 12 first. Once it's done, so 13 is not in the list. They have a common one. So now we have between 16,
14.
16, 15, 14, and 18. So it's 14. How many nodes we are exploring? You see this algorithm, it's trying to execute search, but it has no like strategy or, okay, this is one of the limitations. Okay, but let us reach to the goal first. So which one now? 16, then 18, then 19, 20, 21, 23, 24,
26.
we're reaching to the goal. So we are reaching to the goal mainly after exploring all the like elements, which is like quite time consuming and resources also consume. We found this way first, okay? So once we reach to the goal, we keep the execution of the algorithm because there may be like two different ways, and this is the optimum one. We are finding even first. Okay, now what we have for the homework, I'm going to share this after the class. You will try to execute the BFS like given this problem, okay? It's simple. So what we have here, we have different nodes. We have the S is the initial state, okay? And the goal states are J1, J2, and J3. Then you have different intermediate states which are like A, B, C, D, E, F. That is it, okay? And here, the good thing that we didn't have before is the cost on the rows. So we'll try to solve this problem with respect to the BFS. Okay? Is it clear for everyone, this algorithm? So if you keep in mind, FIFO-Q implies BFS. This is the summary. This is the logic. First in, first out, while exploring whatever problem. If cities, if like we are in the context of a game, even in a tree or whatever. So online, everything is okay? Okay. So now we are going to discuss the complexity of this algorithm. It's given by this like table. So these 4 parameters previously introduced, including the completeness. So this is complete if B is like finite like elements, set of elements. The time consumption here, it's illustrated here. We have in this like triangle pyramid, we have one node on the top, B like square until B power D nodes. So here we will be, until we reach to the goal, we will be going through the sum of all these elements, which is going to be in the order of O of like B power D plus 1. And the complexity, the space complexity, so given here. And is this an optimal solution? Yes, it could be if the cost is equal to 1. Otherwise, so it's not an optimal solution in general. So let's move to the other algorithm, which is the uniform cost search, which is UCS. So in this case, this is the algorithm more known as Dijkstra. And if you have time and passion, go and try to solve some of these Dijkstra algorithms. I do recommend, but I will not include in the grading. So if you will come, like you say, I'm trying to solve some Dijkstra, it will be really appreciated because I try my maximum to make things simple in this class. But I just want you to note that AI is not that simple. So if you really want to enjoy, just go and try to search such algorithms, okay? Because it's real world problems that have different approaches to solve. Like for example, here, what we will have a specific strategy. And I tried to summarize in this course the strategies that I see useful, but there are other different strategies, okay? So we have the strategy here is to expand least cost unexpanded node first, and we are going to note G of n, the path cost function, and then we are going to implement the priority of this function in the queue with respect to the frontier structure, also like with G of n. So what to do in this case, how we are going to approach this problem. We are at arad, so where we can go from here, one of these like states. What you may have here is the actual cost. For example, here it's mentioned on the arrows 140. This is, it's like a distance in kilometer given a particular path. So here I will be considering that the cost, which is that function I'm just introducing, okay? So I have different costs. I have 118, 140, and 75. What are you going to opt for? That's accurate, okay? So next I have 118, 140, 146. What you opt for? 180. 229, 140, 146. No? Oh, yeah. I thought that 75 is free, but yeah, you go for the 140. Always check if this are, for example, connections are skipped or not, but now you are right, okay? So 229, 220, and 146. I don't keep talking. You will just say it. Yes, you're right. 140. Okay? The least. You said 140 or you said 146?
140.
Yeah, means that's correct. So next we have 229, 220, 239, and 146. The least. 146. Okay, that's great. So next we have 229, 220, 239. Which one? The least. 200? 20. Okay. 229, 366, 220, and 239. 20. Then, I don't see this one. So, 366, 317, 239. 70. Oh no, you remember I told you you need to pay attention to that. Okay, what was that? It was 229. Okay, we go for it. So 317, 317, 239, they have like equal values. 200 is the least. Okay, and then 17 that one, then 17 the other one, then 17 the other child, and then the least one, and that is it. Is that clear how we are like visiting these nodes? Each time you are going to consider the path, the cost, the evaluation function that we had, and each time with logics you are going to opt for the less expensive one. And always be careful so you don't forget you need to visit all the charts. Okay, yes, sir.
And what's the name of the algorithm?
Uniform cost.
Yeah, it's the uniform. This is an example, just okay, we go for it. Uniform cost search.
Is it a type of BFS?
No, it's a different one. We were mentioning here, sorry. After BFS quiz. Where is it? Okay. I was mentioning even before, just to make it clear for you, for everyone. See. Where I was. Oh, here. We said that there are two types or categories of search, the informed search and the uninformed search. In the specific category of uninformed search, I have three algorithms selected to see in this class. There are more. So among these three, the BFS, the uniform cost search, and the depth first search. So we will see now the DFS, if I'm not wrong. But before that, we need to execute the uniform based search on a binary tree. So just one moment. We are done with problem solving. So here, we're going to execute this on a simple binary tree. So you go for it. First, we are at A, then A, B or C, we are going for B, then C, then we have D and E. So we are coming to the goal, which is D, which is exactly the same as BFS at this level. So we will execute this uniform like cost search on the maze example. So we go for it. So this is the initial state, and this is the goal, where we can go from the initial state here or here or here or here. So each time you are going to have the subscripts here represent the path cost so far. Okay, so here it's like decides the priority. Same as before. Before we had the distance on the arrows at the end, so now we are having this information. So from this point, as all they have 1, 1, 1 priority, we are visiting in the order. So this is like 2, this having also priority 2, and this having the priority 2, same priority for all the childs. Next, we are exploring for the 2, which is now for the 3, then for the 4, and then we are going to the 6. Okay,
Same thing.
it's same. Okay, we go fast.
Yeah.
Okay, if you all agree, then this is the same approach, and this is the same solution. Okay, but it's not the same strategy because this one is taking into consideration the cost. Okay, the other one we didn't consider the cost, but at this given setting, we are coming at the same point. Given a different algorithm, we may find a difference between both, like in different situations, we may find difference between both solutions given by each algorithm. Yeah,
So this is only the same because the path costs are all equal. Path cost is 1.
yeah, you are right. Absolutely. Yes, Farah,
It's the same.
same question. Great.
Real
And-
quick, you're at a 2-minute warning. Thought you'd want to know.
Excuse me?
It's 4:08. You got 2 minutes left.
Okay, yeah. Thank you very much.
Yep.
So if we are done with this, now we have this table. This is complete. Yes, we are visiting all the states. The time is in the order of epsilon here is the low bound of the step cost, and the C star is the cost of the optimal solution. So this table summarizes the complexity of the time is the order of B like power C star divided by epsilon. Space, it's the same, and it's optimal, yes, because the nodes are expanded in increasing order of G of n. So there are some issues with this like algorithm. So it's okay, it's true, it's complete and optimal, but the thing, it explores options in every direction. So it's like going everywhere, and there is no information about the goal. So we will see in the DFS that a way maybe we can go at a given specific direction, and this will happen thanks to the strategy of last in, first out, the stack. So we will go deep in the whatever, for example, 3 or the search, given search problem. So in this case, let's execute it. So we will go this, then this, then this, and next, what we will do is that we will keep going in a specific direction, deeper and deeper and deeper and deeper until we come to the main target. Is that clear? So in a binary tree, it's the same concept. We are going to visit the elements. We are going not like before, level by level. Here we are going to explore in a specific depth, and then we can come back to exploring the other directions. So is that clear?
Yeah.
If we execute this DFS algorithm on the maze example, so we have from this state, we go to the 4 states here. So we will be visiting in depth, means we will avoid all this, and we will reach straight to the target. Is that clear? We take one element and we keep going. Okay? Yes.
Why did it choose the 4? Was it because it was the last one?
1, 2, 3, 4. Okay, so we were choosing 1, having 5. Yeah, starting with 4, which is the last one. You are right. Yeah. So that is it. Okay. Also, there will be homework published for the DFS. So it's the same thing for BFS and DFS I'm going to share. And this algorithm is still not optimal because we may find other like optimal algorithms. These I'm adding extra, but it's for your kind of knowledge. We can execute the DFS algorithm at any given level of the problem. So each time you will find like a way to execute, you keep executing the DFS, which means you run it with depth limit 1. If no solution, you move to the depth limit 2. If no solution, you keep moving to the depth limit until you will find the solution. So this is the iterative deepening DFS. It's a variant of the DFS. And so here just an illustration of it. So then we will move to the informant search. Informant search is where we have an idea about the goal, where is it? And we may have some logics behind or to follow, for example, to know that the exit is on the left side. If I'm going to the right side, then it's useless. So these algorithms may introduce the heuristic function. This heuristic function is noted by f of n is equal to h of n. And in the particular case of greedy best search, which there it's based on the priority queue, means it will give priority to nodes having a minimum value of the heuristic function, okay? So executing that, here we will be having this list of h of n, which is the heuristic value, the information we are having, okay, available information, which may be the, let me say, the straight line distance. Straight line distance is an additional information given to reach to the goal here. So you know, for example, the straight line distance to the initial point is equal to 366. If we are coming to the goal, means we are there, which is Bucharest here. This is why the heuristic function is equal to 0, means it's done, we are there. So these additional information are going to help. So now, for example, from Arad, we are going to move to this one, then this one, then this one. How to choose after that? Sorry. How to choose after that? You have this in the list. You check the heuristic value of this country, this state, which starts with T, it means this one. It's 329, is that clear? You keep the values, okay? 329, okay, in the list. And this one, sorry, what is it? Okay, this one, CPU, is having the value of H 253 in the list. So we have 229, 253, and the other one is having this one, 374. So we go to the minimum one, which is 253, okay? In the this is the additional information that's going to guide. So this is why we take from, this is the minimum one, we go here, okay? Then again, we keep checking this list of heuristic functions, and we keep following the cities that are having the minimum value of the function h, okay? Because f in our case is equal to h until we reach to the goal. Is that clear, everyone, please? Okay, still we have time online? Okay.
No, we're 5 over.
This is the next. Okay, so I believe that we are done. Next time we will move to the A-star algorithm, and we start the other, like the rest of the algorithms, like gaming algorithm, like min-max and so on. Okay, we are done. If you have any questions, never hesitate to send me emails, and never hesitate to come to my office in the lab. So if you have free time now, we can go to the lab. Okay, so thank you.